Imagine you spend like 4 hours driving this grueling, twisting, 269-kilometer mountain road.
Oh, wow. Sounds exhausting.
Right. You burn a full tank of gas, your tires are worn down, and you are just completely wiped out. But when you finally arrive, a physicist looks at your journey and says, actually, you barely moved at all. You only went 35
Which
kilometers.
is, technically entirely accurate in physics.
It's so frustrating. But welcome to the deep dive. Today, we are looking at the bizarre, just utterly counterintuitive rules of one-dimensional motion and the equations that govern, well, everything in our universe.
Yeah, it's a huge topic.
It is. And we are doing this for you by walking through this remarkably clever slide presentation that we found. It takes all those intimidating chalkboard formulas and turns them into this highly visual, intuitive story.
It's honestly a brilliant way to learn this stuff. Because instead of throwing numbers at you, this presentation uses these shifting visual backdrops to trace the historical evolution of how humans understand movement.
Yeah, the visuals are so cool.
They really are. We are literally watching the scenery change from, the ancient marble pillars of classical Greece, morphing into the polished instruments of the Renaissance, and finally arriving at the modern highways of today.
Okay, let's unpack this. The presentation starts us off way back in the 4th century BC, and the visual is fantastic. There is this very serious, stoic marble bust of the philosopher Aristotle.
A very heavy thinker.
Right, but sitting right next to him to completely deflate that seriousness is an image of a delicate little feather and this wide-eyed cartoon elephant.
I love that contrast.
It's great. This imagery is setting up Aristotle's core premise, which was essentially just common sense. He stated that heavier objects fall faster than lighter ones.
Which, for 19 centuries was just the accepted truth of the universe. Nobody really questioned it.
But wait, I have to push back here on behalf of you, the listener, and honestly on behalf of my own brain. Aristotle's idea feels completely intuitive.
Well, sure it does.
Like if I go up to my roof right now and I drop a bowling ball and a chicken feather, the bowling ball obviously hits the ground first. It hits the ground while the feather is still floating around up there.
Right, right.
So is Aristotle just not paying attention? Why are we framing this foundational philosopher as the guy who just, got it completely wrong?
What's fascinating here is that Aristotle was paying absolute attention, but he was a victim of the very environment he was observing.
Wait, what do you mean a victim of his environment?
Well, he was watching the real world, and the real world is incredibly messy. It is full of invisible forces that corrupt our basic observations. To get past Aristotle's common sense, the presentation fast forwards an astonishing 1900 years to 1564.
Ah, okay, so we're skipping ahead a bit.
A huge leap, yeah.
Yeah.
And this introduces us to Galileo Galilei.
Right, the visual shifts to this gorgeous, bright photo of the 12th century leaning Tower of Pisa.
A classic physics landmark.
Definitely. And the text appropriately crowns Galileo as the father of modern physics and science. And the reason he gets that massive title isn't just because he figured out a math problem.
No, not at all.
It's because he changed the entire method of human inquiry. Like, Aristotle used passive observation and philosophy, but Galileo introduced something wildly disruptive test by experimentation.
Exactly. He essentially invented the scientific method as we understand it today.
Mm.
Galileo realized that just watching the world, passively wasn't enough. He had to actively interrogate it.
You had to make the world prove it.
Right. And the breakthrough highlighted here wasn't merely that Galileo went up a tower and dropped things. The paradigm shift was that when he dropped objects with different masses, say, a dense, heavy cannonball and a smaller, lighter musket ball, they arrived at the bottom at virtually the exact same time.
Oh, wow. So the whole bowling ball and the feather scenario is just a trick of the environment.
Exactly. Galileo realized that the air itself was a physical medium. It was pushing up on the feather, hiding the true nature of how objects actually fall.
So the air was basically running interference.
Yes, exactly. By choosing dense, aerodynamic objects where that air resistance was negligible, Galileo effectively isolated his variables. He proved that gravity pulls on everything equally, and in doing so, he basically discovered air resistance by proving what it was interfering with.
Okay, so Galileo figured out how things fall by experimentally removing the air from the equation.
Right.
But that still leaves a massive glaring question that this presentation immediately pivots to. Like, why are they falling in the first place? What is actually doing the pulling?
And that is the million-dollar question.
So to answer that, the visual timeline moves to 1643, introducing Sir Isaac Newton.
And this is where the scope of our understanding just completely explodes outward.
We get this iconic, almost mythological cartoon visual of Newton. He is sitting under a tree, reading a book, and a bright red apple is plummeting toward his head with a dashed line tracking its downward path.
The classic legend of the discovery of gravity.
Yeah, exactly. But I love what the presentation does next. The very next visual scales up aggressively. It completely replaces the apple tree with this massive, stunning photograph of the Earth and the Moon surrounded by the dark of space.
A huge perspective shift.
It directly connects the apple falling to planetary motion. So here's where it gets really interesting for me. Are these visuals implying that the exact same invisible force pulling a piece of fruit onto a guy's head is the same tether keeping a celestial body from flying off into deep space?
That is exactly what it's implying.
But, like, how did he make that leap?
Well, that synthesis of information is the defining mark of Newton's genius.
Ooh.
Because before this moment, the accepted belief was that the universe was fundamentally divided.
Divided how?
People thought the heavens, the stars, the moon, the planets, they operated by some divine, almost magical set of rules, while the Earth operated by a completely different, mundane set of rules.
Oh, I see. So there was Earth math and heaven math.
Right. Newton looked at the falling apple and the orbiting moon and realized it is the exact same rule.
So gravity isn't just a local weather pattern on Earth.
Not at all. It is a universal law. The mechanism that drops an elephant off a tower is the exact same mechanism holding the entire solar system together.
That is kind of mind blowing when you really think about it.
It is. By connecting the terrestrial to the celestial, Newton didn't just explain falling objects. He gave humanity a unified mathematical framework for all motion everywhere.
Which perfectly sets up the next act of this visual journey. Because now that we have universal laws, we need an actual language to measure and describe this movement.
Exactly. And that is where the presentation introduces us to kinematics.
Kinematics, a term derived from a Greek word meaning motion. Kinematics is the foundational study of motion and its causes. It is essentially the grammar of physics.
That's a great way to put it, the grammar.
And like any language, it has a vocabulary. The presentation boils this entire field down to three core quantities: time, displacement, and velocity.
Let's start with the first one.
Right. It immediately dives deep into the first one, time, which is represented by the symbol T. Now, we generally understand time as how long an activity takes, but there is a specific bullet point on this slide that made me just stop dead.
Oh, the basic philosophy point.
Yes, it reads, Basic philosophy, time is measured in terms of change. So what does this all actually mean? This text implies that time isn't just a ticking clock on the wall independently running in the background. It's literally the fact that the universe is different now than it was a second ago.
It is a profound philosophical realization, and it's embedded right there in the middle of a high school physics lesson.
Right.
In physics, time is fundamentally the progression of events. If you were to somehow freeze every single atom in the universe perfectly still, I mean, if absolutely zero change occurred, no planetary rotation, no atomic decay, no shifting of light, the entire concept of time would become completely meaningless.
Because there is no metric to measure the difference between then and now.
Correct. We measure time by the rotation of the Earth, the swinging of a pendulum, or the vibration of a quartz crystal in a watch. Change is the engine of time. Without change, time doesn't exist mathematically.
Wow.
And the presentation pairs this philosophy with a crucial mathematical classification. Time is a scalar quantity.
Right. A scalar quantity, meaning it only has magnitude. It is just an amount, a size, a duration. 5 minutes is just 5 minutes. It doesn't point north or south. It just is.
Which is relatively simple to grasp, I think.
Yeah, that makes sense to me.
But the moment physical space is introduced into our equations, the presentation shows us how we are forced to deal with a much more complex classification.
And that is the vector.
Exactly, the vector.
And to explain the difference between a scalar and a vector, the presentation gives us this brilliant map challenge. It compares two concepts that sound like synonyms in everyday conversation: distance and displacement.
They sound identical to most people.
They really do. But it defines distance as our scalar quantity magnitude only. It describes the total length an object travels using the symbols x or y.
Right.
But displacement is our vector quantity. It requires magnitude and direction. It describes the location of an object with respect to a starting reference point.
And this is usually the exact moment where students get completely lost in the abstraction. But the visual example provided here anchors it perfectly.
It really does. The visual is this highly specific real world image from Google Maps. It shows a driving route in the Philippines from the city of Iligan to Cagayan de Oro.
I love that they used a real route.
Me too.
Yeah.
The map highlights this blue line following the coastline, twisting, turning, and winding along the highway. And the text points out that the total driving distance on this curvy road is around 269 kilometers.
Pretty long drive.
Right, but the displacement, which is illustrated as this perfectly straight, unbending line cutting straight from point A to point B across water and land, is only about 35 kilometers.
It highlights a massive disparity between the physical effort exerted and the physical change achieved.
Okay, let me play devil's advocate here for our listener because this feels almost insulting to the driver.
Go for it.
If I hop in my car and drive that twisting, winding 269 kilometers,
Yeah.
I burn a ton of gas. I put wear and tear on my engine. I spend hours in the driver's seat. The 269 kilometers is my physical reality.
Absolutely. Your back is going to feel those 269
All
kilometers.
right. But as far as physics is concerned, my displacement is a measly 35 kilometers just because that's the literal straight line gap between the start and the end.
Yep.
By that logic, what if I got so lost I just drove in a massive circle all day and ended up parked right back in my own driveway?
Well, if we connect this to the bigger picture,
Yeah.
yes. If you drive in a massive circle all day, your distance traveled might be 500 kilometers, but your displacement is mathematically zero.
Zero.
Zero. Because compared to your starting reference point,
Yeah.
you have not gone anywhere.
My wallet feels the 500 kilometers of gas, but the universe says I stayed home.
Exactly. And the reason physicists care about displacement over distance is predictive power.
Predictive power.
Yeah. If you want to predict where an object like a rocket, an asteroid, or a ship is going to end up, knowing the total distance it traveled is practically useless.
Oh, I see what you mean.
Right, because 10 steps forward and 10 steps backward is a distance of 20 steps, but a displacement of 0. Vectors matter because direction is the only way we can actually map reality.
That makes a lot of sense when you realize physics is trying to predict the future state of an object, not just audit its gas mileage.
Exactly.
So, building off this idea of distance and displacement, the presentation moves into how we measure the rate of that movement. We get this classic physics visual, a sleek red car moving along a straight path.
We all know the basic difference between speed and velocity from high school, hopefully. Speed is the number on your dashboard speedometer, but velocity is adding a compass to it.
Right.
But seeing how it alters the math on these slides is really illuminating.
The presentation breaks it down so simply. Speed is our scalar. The formula is simply speed equals distance divided by time. It answers the question, how fast is this body moving?
And then there's velocity.
Right. Velocity is our vector. It answers how fast and in what direction. Now, the visual puts up this intimidating formula with X's and T's and little subscripts like T naught and X naught.
Which looks scary at first glance.
It does, but really it's just a story of before and after. To find velocity, you take your final position, subtract your initial position, and divide it by how long the trip took.
It strips away all that intimidating alphabet soup.
Yeah.
It's just where did you end up minus where did you start, divided by the time it took to get there.
And the visual grounds this with a sample problem. A car takes 5 minutes to cover a 20-kilometer road going west. You divide 20 kilometers by 5 minutes, convert to meters per second, and you get 66.67.
A solid speed.
But the conclusion on the screen is what really caught my eye. It says the average speed is 66.67 meters per second, but the average velocity is 66.67 meters per second west.
Emphasizing the vector.
Yes. I have to point out the exact moment the math changes categories. It's literally just adding the word west at the very end of the number. It feels so simple, almost like a formatting trick on the screen.
It looks like a formatting trick, yeah. But in the realm of physics, tagging west onto that number is a vital piece of survival information.
Survival information.
Think about it. It is the difference between knowing you are running very fast and knowing if you are actually running toward safety or running straight off a cliff.
Oh, wow. Well, yeah.
Direction completely changes the fundamental reality and consequence of the movement. A vector tells the whole truth. A scalar only tells half of it.
Running towards safety versus running off a cliff. That completely justifies why vectors get their own special category.
They definitely earn it.
Okay, so we have covered constant velocity, cruising at a steady speed. For the grand finale of this visual journey, we transition to what happens when you step on the gas.
Oh, my favorite part.
Or, to bring it all the way back to the very first visual, what happens when you drop something off a tower? We are talking about acceleration.
The ultimate game changer in the study of motion.
The presentation defines acceleration as a vector quantity that describes the change in velocity over a time interval. The unit is meters per second squared, represented by a lowercase a.
Right.
And it establishes this really simple relationship. A positive A means you are speeding up. A negative A means you are slowing down or decelerating. And crucially, if an object is moving at a perfectly constant velocity, like our red car cruising steadily west without changing speed, the acceleration is exactly zero.
Because, just like our philosophy of time earlier, acceleration requires change. Without a change in velocity, acceleration does not exist.
Then the presentation drops the mother lode on the screen, a slide titled Table 2.1, Equations of Linear Motion with Constant Acceleration.
The big one.
It is a dense matrix of algebraic formulas. It is the part of the lecture where people usually, panic and check out.
But if you look at it not as a math test, but as a toolkit, it is really the crown jewel of kinematics.
A toolkit. I like that perspective. We won't read every algebraic symbol out loud here, but basically, this matrix mathematically connects position, velocity, acceleration, and time in every possible combination. How should a non-physicist look at this table?
Look at it as a time machine.
A time machine.
Yes.
Mm.
These formulas allow you to predict the future. If you know how fast you are currently going and you know how hard you are accelerating, this toolkit allows you to calculate exactly where you will be 10 seconds, 10 minutes, or 10 years from now.
That's incredible.
If you are missing one piece of the puzzle, these equations let you find it.
A mathematical time machine. But the final visual in the presentation is what truly blew my mind. It's titled Free Fall.
Bringing it all together.
It brings everything full circle back to Galileo and his leaning tower. The text shows us that we simply take all those horizontal red car equations we just learned, and we replace the A for acceleration with G for the acceleration of gravity.
Which is a
Right, it provides the magic constant for gravity, negative 9.8 meters per second squared. We swap out the horizontal x-axis for a vertical y-axis, and boom! Suddenly, the car driving down the highway equations become the exact math needed to calculate the fall of the elephant and the feather.
And this raises an important question about the elegance of the universe, really. What this presentation just revealed is that reality doesn't have different rule books for different directions.
So this whole journey was a setup. We started with dropping things in ancient Greece, we moved sideways with a red car to learn the modern math on the highway, and then the final visual literally flips the car math vertically 90 degrees to solve the very first tower problem we talked about.
It is a beautifully synthesized system. The laws of horizontal motion are the exact same mathematical laws as vertical motion.
That is just brilliant.
Once you understand the toolkit for a car driving west, you simply rotate your perspective, plug in gravity, and you instantly understand how an apple falls from a tree or a rocket launches into space. It is a completely unified theory of movement.
A unified theory. That is just incredibly satisfying to see unfold. What an incredible journey this presentation took us on today.
It really was.
We started with Aristotle's incorrect but completely understandable guess about heavy things falling faster. We stood with Galileo to isolate variables and discover air resistance. We sat under the tree with Newton to connect the falling apple to the orbiting moon, synthesizing the heavens and the earth.
A busy afternoon.
Right. We dug into the philosophy of time, proving it only exists if things change. We debated the real-world value of a 35-kilometer displacement against a 269-kilometer gas bill. We added the word west to a red car to turn a scalar into a vector. And finally, we arrived at a time machine toolkit that proves driving forward and falling down are governed by the exact same mathematical poetry.
It is a masterclass in building foundational knowledge, layering concept upon concept until the complex math suddenly feels incredibly intuitive.
Absolutely. And I want to remind you, if you want to view this incredible source presentation yourself, to see the Google Maps, the red car, and to actually read the math in that ultimate toolkit with your own eyes, you can send an email to dieslearningstuff@gmail.com.
Highly recommend checking it out.
Or you can jump on YouTube and search for Dies at Just Gambe. Just a quick note from the creators. Please don't forget to use your school email, and be sure to write your complete name and class section when you reach out.
The visual representations really do solidify the equations, especially when bridging that gap between the horizontal car and the vertical freefall.
They really do. Well, before we wrap up this deep dive into the language of motion, my expert friend, do you have a final thought to leave our listener with today? Something to chew on based on all this kinematics we just unpacked?
I do, actually. We spent a lot of time establishing that displacement requires a starting reference point, right?
Right.
You need a definitive point A to know how far you've been displaced to point B. But consider the physical reality of our universe. The Earth is constantly spinning on its axis. Okay,
Yes.
simultaneously, the Earth is moving in a massive orbit around the Sun, and the Sun itself is hurtling through the Milky Way galaxy, which is continually expanding outward through the cosmos.
Oh, I see where you're going with this.
So, if every single reference point you could possibly choose is in constant rapid motion, is any object in the universe ever truly at zero displacement?
Oh, wow. So even if I sit perfectly still in my chair right now, doing absolutely nothing, I am currently flying through the cosmos at hundreds of thousands of miles an hour.
You are constantly being displaced on a cosmic scale, whether you step on the gas or not.
On that mind bending, slightly dizzying cosmic note, we're going to sign off. Thank you for taking this deep dive with us. Keep questioning your reference points, keep testing your intuitive assumptions like Galileo, and we will catch you on the next one.